In Chapter 12, we're going to take a look at another macromolecule or biomolecule, lipids. These are high-density lipoproteins, so you can see they have a very architectural shape, and they're beautiful in a lot of ways. Lipids are often associated with steroids. We're going to learn a lot about steroids with this chapter. When we think steroids, probably we consider anabolic steroids first in our mind because we see it in the news. So in 2013, Lance Armstrong was stripped of all his 7 Tour de France titles. When you have the yellow shirt on in the Tour de France, that means you're in lead for the day. He was on steroids. He was a cancer patient, and so he argued that those steroids were important for his treatment, but he was voted down, and they said he had an advantage. So the unique structure of steroids can be easily identified with 4 rings here, and then they also have derivatives coming off of them. We're going to take a look at some of these. This is a very disturbing image, in my opinion. But steroids belong to a class of lipid biomolecules. The male and female sex hormones, estrogens, and androgens are types of steroids. Testosterone is the sex hormone responsible for development of male sexual characteristics during puberty. This is called the androgenic effect. When testosterone binds to the androgen receptor, it initiates a cascade of biochemical events resulting in protein production, increased muscle growth. That's the anabolic effect of steroids. But this is a natural steroid. And there are all sorts of other molecules in the body that are derivatives of testosterone. So anabolic steroids, unlike testosterone, they're synthetic compounds, so man-made. They mimic the effects of testosterone-related hormones because they bind to androgen receptors and initiate the same cascade of events. So they can be very powerful and have sometimes very unintended results, or they can be used to really effectively treat certain imbalances in the body. The chemical structure of anabolic steroids resembles the structure of testosterone. So here is testosterone. You can see they both have that 4-carbon ring structure. Testosterone has a ring with a double bond and a carbonyl coming off of it. Stanozol has like a nitrogen ring coming off of it. So they're derivatives, but they have some similarities. Steroid use, this is synthetic, anabolic, illegal steroids. They can lead to liver damage, prostate cancer, cardiovascular disease, and in adolescence it can stunt your growth. So another concept that we associate with lipids is the ability to not dissolve or be insoluble in water. Water is very polar, and like dissolves like, so oil, it stands to reason, is nonpolar. And that's why it beads up, because it's trying to get all of its most hydrophobic parts balled up inside the water, because it does not like the water. So there are several types of lipids. Lipids is actually a pretty diverse group. There are triglycerides that are molecules that provide the body with long-term supply of energy. There are phospholipids and glycolipids, the main component of mammalian cell membranes. Steroids derived from cholesterol, such as sex hormones, vitamin D, and bile salts. And then there are eicosanoids that are signaling molecules that initiate physiological effects. This is the inflammatory response to trauma and infection to protect your body. We're going to talk a little bit more about triglycerides in chapter 15 when we talk about how cells make and use energy. So fatty acids are an important component of many lipids, so that's what we're going to look at first. You can see the fatty acid chain long here. So they're long chains of straight hydrocarbons. They have a carboxylic acid at one end, which is the red balls here. They contain even number of carbons and are characterized by their level of saturation. So saturated means they have no double bonds, which means they're saturated with all of the hydrogen bonds that they can make. If the carbon is not connected to a hydrogen, if the carbon is not connected to another carbon with a single bond, it has, remember, up to 4. It has to have 4 bonds, and then 2 of them are hydrogen. The one at the end has 3 because it's only connected to 1 carbon. Monounsaturated fatty acids contain a double bond, and then polyunsaturated fats contain multiple double bonds, and that changes the characteristic and the structure of the molecule. For example, you can see it bends. Double bonds bend molecules. So the unsaturation or saturation level of a fatty acid determines its shape and properties. The unsaturated shape also depends on whether the double bond is cis or trans. The difference between cis and trans is that two hydrogen atoms are on the same side of the double bond, because remember, we don't have free rotation about a double bond, it's locked in place, so it stays there. Opposite side hydrogens would be a trans. It doesn't seem like a huge difference, but it makes a kink in the fatty acid. So in a cis trans, you can see it's a big kink, whereas opposed to the trans, it's a little bit less exaggerated of a twist. And then unsaturated with no double bonds, it's a straight chain. So that also affects its boiling point and its melting point. Most saturated fats are solids at room temperature. Oleic acid is unsaturated like many plant lipids, and so it's usually liquid at room temperature. And you can see the trans double bond making it pretty straight. It actually makes lactic acid pretty high melting point compared to oleic acid. So most naturally occurring unsaturated fatty acids contains cis bonds. That's what's found in nature. Trans fatty acids adopt a linear shape similar to saturated fats. The shape of the molecule, it dictates its physical properties. The melting point is affected by intermolecular forces. So since these are nonpolar, they're not going to have hydrogen bonding, but they are going to have dispersion forces and sometimes dipole-dipole. They do have a polar head, so that does make a difference as well. The stronger the intermolecular forces, the higher the melting point. So you can see for linoleic acid, it has a low melting point. It's got cis double bonds and it's twisted. Oleic acid is comparative in size. It's got a melting point of 13. The cis double bond, that's just single. Linoleic has 2. And then no double bonds makes the melting point even higher. This is stearic acid at 79 degrees Celsius. So fatty acids with more carbons have higher melting points because they have more surface area and higher dispersion forces. Cis unsaturated fatty acids have lower melting points. They're straighter. The bends in the molecule lowers the point of contact and lowers the dispersion forces. The more double bonds a fatty acid has, the lower its melting point is the trend there. So you can see as we go down from myristic to arachidonic fatty acids, we increase in the number of double bonds and the melting point goes way down. So salmon, tuna, and herring, they have a lot of unsaturated fats in their bodies, kind of acts as an antifreeze to keep them alive and healthy. Their tissue is functioning well in cold waters. Linoleic and linolenic acids cannot be synthesized by the body, but these are essential fatty acids. You have to get them through your diet. These include omega-6 and omega-3 fatty acids. So there are 2 naming systems that indicate the location of the double bonds. Nutritional scientists use the omega system. Numbering begins at the end of the hydrocarbon chain. Chemists use the delta system, where numbers begin at the carbonyl compound, because organic chemists, the functional group is the biggest factor in dictating chemical nature of the compound, so we give that priority and we start with 1. But here we have flaxseed, walnuts, salmon, canola oil are some good sources of these fatty acids. We're going to look at some examples on Monday. We're going to do one more section, the triglycerides, energy storage lipids. Triglycerides, or simple fats, are the most abundant type of lipid obtained through the diet. Triglycerides are stored in fat cells. These are called adipocytes. Adipose tissue is fatty tissue. It lives on like some of the padding parts of your body, like your hips and your buttocks, but it's also, you have a lot of fat inside your yellow bone marrow for energy storage. Diets in high saturated fats and trans fats have been linked to cardiovascular disease, diabetes, and cancer. American Heart Association recommends a diet low in saturated trans fats. This is the chemical structure of triglycerides. So this is a triglyceride being formed from a glycerol molecule, which is a 3-carbon, and fatty acid, palmitic acid in this chain. So we have the shape here. This is what I use to represent, like if you hold up your hand, your 3 knuckles represent the triglyceride chain, and then the fatty acids are your fingers coming off of it, is kind of a good way to remember the structure of triglycerides. So they're named for their structure. 3 fatty acids are S-terrified to a glycol backbone. So it's kind of allows them like a structure, stabilizing, connecting structure. They're derived from saturated fatty acids, and they tend to be solid at room temperature. They're often called fats. They have higher dispersion forces, so they have higher melting points. They're found in things like whole milk cheese and lard, mostly animal sources for these, but there are some exceptions. Coconut oil and palm oil are solid triglycerides, but they do contain saturated fatty acids. Triglycerides derived from unsaturated fatty acids tend to be liquid at room temperature. They're commonly called oils. This is due to lower dispersion forces because they have more carbon-carbon bonds, less hydrogen interactions between the chains, and they bend the chains. So it takes their interactions away from each other. So this is olive oil, which is kind of a token. We'll look at more examples. Dietary fibers, or digestion of dietary fats. Triglycerides stored in fat cells provide long-term energy. An average adult male stores about 15,000 grams of triglycerides. Glycogen, which is stored carbohydrate, provides short-term energy. An average adult male stores about 300 grams of glycogen. These stores will last about a day. Triglyceride stores will last several weeks. This is glycogen, and then this is adipose tissue. Fatty acid catabolism is the process of energy-producing pathways for many cells. It provides 80% of the energy needed by the hearts and liver, which work hard all your life, nonstop. Triglycerides provide more than double the energy of carbohydrates and proteins. Fats provide 9 calories per gram versus 4 calories per gram for carbs and proteins. So just as the triglycerides can be made from fatty acid chains and glycerol, they can be unmade by hydrolysis. So your triglycerides are digested in the small intestines. When they're from your diet, they enter the small intestine as large globules of water-insoluble fats. The triglycerides are too large to cross the cell membrane of the cell lining intestinal mucosa. The globules are turned into a colloid of finely dispersed microscopic fat droplets suspended in water. This process is called emulsification. So it breaks it down into smaller pieces so it can pass through a membrane. Emulsification requires biosalts. There's a release from the gallbladder after a fatty meal. Biosalts mix with fats to form an emulsion, allowing lipases to hydrolyze them into glycerol and fatty acids. The glycerol and fatty acids are small enough to enter then the intestinal mucosa. Inside that intestinal mucosa, so your intestines have mucus linings to protect itself from destroying itself with all this digestive juices and enzymes. But once inside these emulsified bits of triglyceride, they get esterified back into triglycerides and packed into chylomicrons. and then they're carried throughout the lymph and circulatory systems to target cells. Chylomicrons are the largest of the lipoproteins. So triglycerides are not soluble in water, so they're transported by special lipid carriers called lipoproteins, because they are like a non-polar in a polar environment, so they are kind of enemies, if you will, of water and moving through it. Lipoproteins are spherically shaped assemblies of lipids and proteins, hydrophilic on the outside. That's what's exposed to the aqueous cell and extracellular matrix. Hydrophobic on the inside, so all the really, really nonpolar parts stay on the inside. At the target cells, adipocytes are fat storage cells, liver or muscle cells. Triglycerides are again hydrolyzed for transport into the cell and then converted back into triglycerides and stored or used to generate energy. Okay, we'll pick up with section 3 in class.